Hello, my name is Richard Gwynn, and I'm an undergraduate geology student at the University of North Carolina at Charlotte. I'll be graduating this May with a BS in geology, and in the fall I will be attending Western Washington University in Bellingham, Washington, to obtain a master's in geology. For this project, we hypothesized that mineralogy and grain size characteristics do affect weathering, and in order to study that, we studied the Supraglacial boulders of the Antarctic dry valleys. For acknowledgments, I was selected to work on this project by the Office of Undergraduate Research here at UNC Charlotte through the Our Research Scholar Program. I was assigned to Dr. Missy Epps, who is the mentor and project lead for this, and by doing that, I ended up falling under her NSF grant as well, which is listed. I also worked very closely with Dr. Valerie Reynolds, who is also of UNC Charlotte, and she is a mineralogy and petrology subject matter expert at the university, and she helped ensure that I got my mineral identification correct, as well as the data that I was using, or the thin sections that I was able to look at, came from samples directly collected by the people shown there of the Beacon Valley research team. So, does mineralogy and grain size control mechanical weathering? Well, in order to do that, we needed to see where we're going. And as you can see here, it's already labeled Mullins Glacier. And this is Mullins Glacier, and this is the Beacon Valley where it's going to head in. This is the head wall that these rocks are falling off of. You'll notice this glacier is not white, and you can see some white remnants. That's because so much debris is falling off these head walls and riding this glacier long-term and relatively undisturbed. They were all pretty bedded in there. So the reason that we want to study this is because it's very dry and cold. And a lot of weathering that we know of is mostly based off of water. And so with the absence of water, what happens? This research has already been started by Dr. Epps. She's done research in the Gobi and Mojave Desert, as well as used Mars data to help prove thermal cracking. So this is dolerite and dye-based superglacial boulders. Like I was saying, they're falling off these head walls. The rocks are incredibly similar, and they do not crack very well. This is a view of being on the ground. You can see it's little treacherous terrain, but these rocks are riding this glacier, and they are not moving. So who cares? Well, crack is the beginning for all things in the geomorphology field. There wouldn't be any soil without a crack. That's how soil is formed, how grain size is determined. And very little is known about mechanical weathering. So this image here is from the Perseverance rover. And as you can see, there's a lot of cracks in the rock. Well, what would have caused that with no water on Mars in the last long time? And there's not many other drivers. The atmosphere is 1/100th. So what could cause it? And that's where this stuff links. And not only that, but we'll also, by studying this, also learn more about warmer and wetter climates and how to prevent cracking. So here's just some of the fields: planetary studies, soil sciences, geomorphology, climate change, and then cracks are definitely going to be a big thing for carbon sequestration in our future. So how did I measure these cracks and why? So the crack measurements here, you can see this one running north to south, and this is a good thing of showing that this is only one crack in a thin section, and that's what I studied, was thin sections of the boulders that were collected, not the actual boulders themselves. The image here shows a void as well as a dye. The dye running north to south, that is what was put in the thin sections so we could see the cracks better. And as you can see, it is that neon blue, and we're working on other ways to make it pop even more. So neon blue is in the voids, and that's how we're able to tell. The basic definition of a crack that I'm using for this is that a crack is going to be longer than it is wide. However, a pore would be wider than it is long. So the crack dimensions were going to be measured in micrometers. That's just an arbitrary line software tool that the microscope had. It was very convenient and useful, but all the crack links are in micrometers. Orientation is going to be based off of degrees off of north. In order for me to be somewhat accurate in recording the orientation of these cracks, I did every 10 to 15 degrees off of 0 being north, 180 being south. So a crack running from the northeast to the southwest would have a crack orientation of about 35 to 55. All right, so that was the cracks. Well, how did I acknowledge the mineralogy? So there was, in order to be statistically significant, we decided to do 500 point counts per slide. There was 27 samples that I used, thin sections, and so I identified just over 13,500 minerals. We ended up breaking them into 7 different mineral groups. Plagioclase, which is not listed but is in every image, is this milky white substance here. And then the other one's clinopyroxene right here. Altered green, which we believe to be serpentine. It is a lot more green in the microscope. I wish I could help with that. Altered brown, which we believe to be Iddingite right here. And then we also have olivine, opaque mineral, and then the ground mass here. So we also measured the length and width of every 10 grains. So every 10th grain, I'd measure the length and width in micrometers. And then again, I would multiply those to get the grain surface area. All right, so this is the relative dating technique. This is what I'm going to, so you can see our head wall here. If you remember our image, we were looking here, looking into the glacier. And so this is where the rocks are falling off our head wall, and they're riding this glacier, and they're riding it down and down and down. And so what I did was use an arbitrary line system that measured the distance from the head wall from where the rock was sampled, and I gave it a relative age, or like a relative exposure age. I utilized that by the GPS coordinates that were taken as they collected each sample. Some of these will be a little off, but we do have some proof, and we'll actually have some cosmogenic dating in the very near future that'll make this much more accurate. But I used the glacial movement on average from a prominent research from Ringdo and others in 2002 that concluded that the glacier is moving about 15 millimeters per year. All right, so here's the modal mineralogy for the entire, all the samples. So you can see it's kind of just a hotspot, but it's a cool looking graph. So what you'll notice is that the mineralogy is very similar. There is almost no change through time, meaning that there is not a relationship between mineralogy and time. In other words, as time goes forward, the mineralogy is not being changed. However, cracks did change, so that begs the question of, well, what's causing the cracks to change if the mineralogy is not changing? So we looked at some of the more characteristic things of mineralogy versus the number of cracks taken. And so for a positive correlation, we see altered brown here. It's got a relatively low R-squared value, but its two-tailed p-value is 0.1. And those numbers look relatively low, but when you think about how many samples here are riding on these 0 cracks, and just because the thin section that I have doesn't have a crack in it, doesn't mean that the sample that was collected doesn't have a bunch of cracks in it as well. And so there will be some more ways to look at this in the future, hopefully to get a little bit better data. But there are some correlations. Like I said, this altered brown goes up, which is interesting here because the alteration, or this altered brown mineral, is actually the alteration of cladoproxene. So this negative relationship is actually just making sense to show that when altered brown is going up, it's using up the cladoproxene. So those graphs make sense. Same thing as ground mass. And one thing I did notice with the ground mass as well, the larger cracks tended to be in more ground mass dominated samples. But we look forward to continue looking into this. So grain dimensions versus the cracks. So this is going back to when I took the grain size of every 10 grains. And as you can see, there's plenty of samples with 0 cracks in them again. But as grain size goes up, the cracking seems to go up or correlates with that, at least a positive relationship. And we could take that well as well because of a few things. Well, one, it just makes sense. The more surface area there is, the more area there is to be eroded. So that we can kind of follow that. So another thing to look at is that the cracking and porosity is going to increase with the relative exposure age. And this is going back to the measurement tools that I did on Google Earth earlier. So this is both making sense. One, that the longer something is exposed to atmospheric or weather conditions, or any condition in general, the sun or the wind, you're going to see a increase in cracking just because there's been a longer time for it to happen. All right, so this is the interesting one. This is cracking orientation. So this orientation, it is in a rose diagram, and you can see that it's already kind of crazy, but it is kind of leaning towards the northeast, that 35-degree mark. So there's also another maximum here going from northwest to southeast, and then another one southwest to northeast that we just talked about. So, but there's also this radial pattern. So I would say that it's weakly favored to the northeast, southwest, northwest, southeast, which are the two largest thermal directions, just afternoon, as in like 1 o'clock, and then sunset. But you'll notice that radial pattern that I've brought up a few times. And remember that Antarctica also has 24 hours of light and 24 hours of darkness periods throughout the year. And I'm hypothesizing and going to look into further that this may be from the sun staying in the sky for 24 hours and rotating around and creating thermal stresses that last longer. And so it's just going to have more randomized things. This also could be that the crack was on the rock before it fell off of the head wall. It could be from a few other reasons. So we're just going to look into that a little bit further. So for conclusion, rock cracking does appear to be influenced by time, mineralogy, grain size, and insolation. Insolation being thermal energy from the sun, as we talked about in the last slide. So, although the presence of ground mass and ultra brown minerals have positive relationships to the amount of cracks, the low P scores in both of those would indicate that mineralogy has less to do with cracking than some of these other ones, but still might be just a small part of the picture. Thank you much for listening, and look forward to questions.